This is Algebra 2 with trig, 6.2, day 2. We're talking about the properties of rational exponents and the radicals, and we're going to have variables involved with that. When it's an odd index, we can get a value that's either positive or negative. But when it's an even index, what comes out has to be a positive number. So the cubed root of 25 is 5. The cubed root, or the square root of 25 is 5. The cubed root of negative 8 is negative 2. Okay, we're going to simplify each of these. So this is the fourth root, 625. That is 5 times 5 is 25, times 5 is 125, times 5 is 625. Then we would have 12 z's. So that would be 4 of them, 8 of them, 12 of them. We're looking at the fourth root. So essentially we're looking for 4 of a kind, another 4 of a kind, another 4 of a kind, and another 4 of a kind. There's 3 of those, so we put a 3 up there. So this simplifies down into 5 times z cubed. The 1/5. Essentially, that's the same thing as the fifth root. But with it being an exponent, we can multiply all of our exponents. So we're going to get 32 to the 1/5, m to the 5 over 5, and n to the 30 over 5. Well, the fifth root of 32 can be written as 2 to the 5th. That's the same thing as 32. This becomes m to the first power. This becomes n to the 6th power. So this is going to be 5 over 5, which is 2 to the 5 over 5 power, which is just 2 to the first power, m, n to the 6th. Here we're looking at 2 different bases, so we can't add or subtract. You can't do any combining there. But what we can do is we're going to look at this as the 6th root of r to the 6th over the 6th root of s to the 18th. Well, this comes out to be just r. How many groups of 6's of this type are there? There are 3 of them, because 6 times 3 is 18. That's an S, not a 5. Here, a little bit more complicated looking. When our bases are the same, and you're doing division, we can subtract exponents. So I'm rewriting this so that each of our terms is represented with a separate fraction. So the 56 and the 7 come out to be 8. This is a 1 minus 5/6. This is still b to the 3/4. And this would become a positive 3 up on top. So we have our 8. If we were to subtract this, it would be 6/6 minus 5/6, which gives us 1/6. We still have 3/4, and we still have 3. Now what we need to do is get all the denominators the same. So we have the 8, we have the C3, but here we have denominators that are different. They can both go into 12. So we're going to take a to the 12th. That should be a 12. And b to the 12th. To get the 6 to become a 12, we've got to say times 2. For the 4 to become a 12, we've got to say times 3. So what that's going to give us is our 8C3. We have the 12th root, because now we have the same denominator, which gives us the same index, of a squared b to the 9th. That was a bit of a tricky one. We had to turn the denominators the same so we could have it be the same index for the radical, so that we put them all underneath the same one. We don't want to have them under separate radicals. So we're just going to simplify away here. This is the cubed root. So we're looking for 3 of a kind. So here we have 4 x's. Here we have 9 y's. Here we have 14 z's. That's a whole bunch of them. Now this is a little middle schoolish by breaking them all down like this, but whatever you see, and I'll talk you through how to do this without writing them all out. Okay, there's only a 6, which is a 2 and a 3. There's no 3 of a kind there, so we'll leave it a 6. 4 of them. 3 goes into that one time, so we know we're going to have an x come out. You're going to have 1 left over. 3 goes into 9 3 times. It goes in there evenly with none left over. So we're going to have y cubed sitting on the outside. And then 3 goes into 14. It goes into there 4 times. 1, 2, 3, 4 times. So we're going to have z to the 4th power. But we're also going to have a z squared left behind. So in this case, we have more p's than we need. We have 8 of them. We only need 7. So we're going to be able to pull 1 out. And that'll leave 1 behind. Here, how many more q's do you wish you had? You wish you had 7 total. You currently have 5. So to rationalize the denominator, we need to come up with 2 more q's to give us a total of 7 q's on the bottom. So now, no, I'm sorry. Whatever we do to the bottom, we also have to do to the top. So in this case, we're going to have the p, the 7th root of pq squared. That's what happens when you multiply these together. If the indexes are the same, you can multiply p and q squared. On the bottom, we're going to have the 7th root of q to the 7th. So that's going to leave us with p, the 7th root of pq squared all over q. That looks like a tough one too. Let's look at our like terms. If we're adding and subtracting, we can only do that if the terms are like. So the radicals are like if the indexes are the same and the radicands are the same. We have 18 minus 11, which gives us 7. So essentially, this is like 18x minus 11x. We would call that 7x, which is, in this case, 7 cubed root of u. Here the 4's match and the b's match. So they're again like terms. So we can say 15 plus 8, which is 23. So we say 23, a to the 4th, b to the 2/3. Those are like radicals because they're exactly the same. But if we look at this last one, they're not exactly the same. The indexes are, but what's inside is not. We have a 5. We have s to the 7th. So s to the 7th is telling us that there is more than 4 of them. There's actually 7 in there. So if we need 4 of them to pull one out. And that's going to leave us 3 s's still inside. With the 80, we're going to call this 80 is 8 times 10, 16 times 5. 16 times 5 is 80. 16 is the 4th, 2 is to the 4th power, gives you 16. So we can pull out a 2 because there would be 4 2's in here. And then there'd be another 5 left over, but there'd still be 3 s's. So now you see we have like terms. We had to simplify, so we had like terms. We have 10 s's minus 2 s's, which gives us 8 s's, the 4th root of 5s to the 3rd.